All right. So guys, our learning goal for this week is that we can explain the law of conservation. Now, guys, I would like everyone to pay attention, please. Otherwise, um, I would just take your chat privilege away. Okay? Okay. Right. Let's go. So our learning goal is that we can explain the law of conservation. Okay. So let's unpack what it means. So here's some of the rating, guys, that to help you with with your own rating of the understanding. So the first one there is that, um, we know what, sorry, we know where energy comes from. Okay. So if you know that, then, you can give yourself a one. If you know that energy cannot be destroyed, right, James, my friend, I need you to pay attention, please, and let everyone else learn. Okay? If this keep going, I'll move you to the lobby. Okay? All right. So if you know that energy cannot be destroyed, then you can give yourself a two. And if you know what the law of conservation is, then you can give yourself a three. And then if you can also explain a little bit about it and give examples, then that is a four. Okay? So hopefully you guys have rated yourself on your understanding. Now let's talk about APK here. All right. So APK, you can see there we got a bowling ball um, striking some pins. So what I would like you to talk about, okay, just have a think about it. You can type this in chat. Jada, you can tell me the answer if you know. Um, but I want you guys to think about, what happens to the energy here, right? What happens to the energy as it goes from the bowling balls to the pins? Okay, so have about 1 minute to think about it. All right, and then we talk about it. Jada, what do you think? What do you think, Jada? What do you think about the bowling pin and the bowling ball? The bowling ball and the pins. A lot of force, yeah. So Jada just said that the bowling ball has a lot of force. What else there? Um, Nam said is two bowling pins. What do you mean by that, Nam? So we can see here. That's okay, Nam. So that's all right. You can give it another try. Oh, it's because the animation stopped. Okay. What kind of energy can we see here in this animation? Last we learned about energy types. What kind of energy can we see here? Gabe said forces. James says rolling. Also friction. Adam said kinetic. Adam, well done. Kinetic. Definitely kinetic energy in there. Can you can you repeat for everyone what kinetic energy is about? You can type it in chat or Adam said it's the energy that moves an object. Good job. Yeah. So we can see we can see that the bowling ball is moving, right? The bowling ball is moving towards the bowling pins here. So it's going to have kinetic energy, right? And then what happens is that it just, when it hits the pins, the pin is struck away. So the pins themselves, they move after being struck. So that means that they have kinetic energy as well, right? Um, and it's, if you guys ever go to a bowling alley, what else happens when a bowling ball hits a bowling pin? Maybe something that, think about, apart from the pins being knocked away, is there anything else that happened at the same time? Adam said sound. Good job, Adam. That's another thing, right? So, so the bowling pins, they are struck, right? They struck, they fly away. At the same time, you probably hear the sound of the pins being struck. And we know that from last week is that sound is another type of energy. Okay? It's also a type of kinetic energy because sound is the movement of air. Right, guys? All right. So basically we're talking about, the energy, and what's happening here is that the bowling ball would gives its energy to the pins when it strikes the pins. Okay? So let's talk about this. Actually, I want to show you guys this video because it's quite an interesting one. Let me. All right, share video. Blah blah blah. Okay, let me set things up again. Sorry, guys. Okay, and everything is recording. Recorder. Yep. Okay. So, guys, let's watch this video now. Don't try this at home, okay? If you want to, we can do this when you guys get back to school, but don't try this at home.
I am such a strong believer of the conservation of mechanical energy that I am willing to put my life on the line. If I
All right, guys, sorry about that. I just needed to set up the sound so that Jada can hear it. Okay. All right, it should be good to go now.
of the conservation of mechanical energy that I am willing to put my life on the line. If I release that bob from a certain height, then that bob can never come back to a point where the height is any larger. If I release it from this height and it swings then when it reaches here, it could not be higher. There is a conversion from gravitational potential energy to kinetic energy back to gravitational potential energy, and it will come to a stop here. And when it swings back, it should not be able to reach any higher, provided that I do not give this object an initial speed when I stand here. I trust the conservation of mechanical energy for 100%. I may not trust myself. I'm going to release this object, and I hope I will be able to do it at 0 speed, so that when it comes back, it may touch my chin, but it may not crush my chin. I want you to be extremely quiet, because this is no joke. If I don't succeed in giving it 0 speed, then this will be my last lecture. I will close my eyes. I don't want to see this. So please be very quiet. I almost didn't sleep all night. 3, 2, 1, 0. Physics works, and I'm still alive. See you Wednesday.
Okay. Nam said he's already noticed. Well, good for you, Nam. You know, like, but let everyone else watch this because they may have not. Kids in the background with fingers crossed. All right. So, okay. You think that everyone should know this? Yeah, everyone should know it, but not doesn't mean that everyone would know it, right? What's going on here? Sorry, guys. Oh, now it's working. Jeez, how fun is that? All right. Okay. So the law of conservations of energy. Okay, guys. So here's some of the notes that you would need to write down. Again, guys, just try to summarize the notes here and just pick out the things that was really important, right? Okay. So so think about the word conservation, all right? Just in normal English, right? When you hear the word conservation, what does that mean? Conservation. I know it says right there, but just in normal English, right? Just in our everyday normal English. If we talk about conservation, not conversation, Nam, it's conservation. It's a bit different. um, so conservation. So when it says, I'm conserving my energy, for example, what does that mean? Okay, preventing something from being wasted. So conservation is that it's not that you want to use up your energy, it's that you want to keep conserve it, right? You want to keep as much energy saving. That is a good that's a good that's a good word there, Gabe. Saving energy, right? If you want to conserve something, you want to save it. So the same, so that's what's happening here, right? So when we talk about law of conservation energy, we're talking about the fact that energy cannot be created or destroyed. Okay, so I would say that this bit here is really important. Energy. Oh, I use a different color. I'll probably use a different color here. So, like energy cannot be created or destroyed. Okay? That's really that's the important bit here. That's conservation of energy. So, and then what it says that if all the input energy could be added and compared with all the output energy, it would always be the same. The total energy remains constant, but the type of energy will change. Okay, so it can change, and what goes in must come out. Okay, so I guess the other bit that may be important here is that the total energy remains constant, but the type of energy will change. Okay, that's the other important bit there. Bye, Jada. Jada's gone. Okay, so like you may have seen something like this before. This is called a Newton's cradle, and with a Newton's cradle, if you got a little ball, and just it's gonna strike another, some other balls, and they just keep going back and forth. So what I'm saying is that energy has been transferred from one ball from a different ball. Okay, and what goes in must come out. That's sort of like everything in life, right? James, I know, mate. Okay, let's move on. All right, so if I was to summarize this, okay, energy cannot be created or destroyed, and the total energy remains constant. That means that it remains the same, but the type of energy will change. Okay, so moving on. All right, this is an animation, and I think I need to read something here. Okay, so what this animation is showing you is that when you lift an object into the air, okay, you're adding gravitational potential, right? We learned about this last time. Now, the thing is, this energy did not just come from nowhere, okay? What happens here is that the what we're doing is because we're moving, right? We're moving the box. That means that we are giving it kinetic energy. And then that kinetic energy then changes to gravitational energy. Okay? Now, when we drop the box, the reverse going to happen. What's going to happen is that when we drop the box, the gravitational potential energy inside the box is released. And then like Nam said, it's going to go down. It's going to move. So gravitational potential energy then becomes kinetic energy. All right. So you can see that it changes between kinetic and potential, and then from potential back to kinetic. Okay. So moving on here. All right. So now the thing is, right? Um, Did you notice that when the in that video with the professor before, when the bowling ball came back to him, it didn't, sorry, he released it right here, right? Right against his chin. But the bowling ball didn't come back all the way to his chin. It come back to like this much. So why is that? Now, if you so could you say gravity and things? Um, Maybe it got to do with energy and speed. Now the thing is, we just learned that energy cannot be created or destroyed. So that means that if I release the ball right here, it should come back here because the energy should be there, right? Now the thing is, right? The thing is, in real life, in real life, something that James said before. In real life, there's things called friction, and there's things called air resistance. What's going to happen is that what's going to happen is that some of the energy would be changed into heat and sound energy, as you can see on the slide. Okay, so sound and heat energy are often generated as a result of energy transformation. The word transformation there, transform, means to change. Okay, um, and the thing is, with sound and heat, a lot of the time you can't use it for something else. You can't use it for some. They're not useful sometimes, right? Um, say for example a car. When you're running a car, the only thing that you want is the engine pushing the car forward or maybe backwards, right? You don't want the engine to create sound because you're not using the sound for anything. So a lot of the time they are called wasted energy. Okay, they're not destroyed. The energy is still there. The sound energy is still there. The heat energy is still there. But they're called waste energy because we're not using them. All right. Now, efficiency. Okay. Efficient transformation produce less waste energy. So the more efficient something is, the more efficient an engine is, the less heat it's going to produce, the less sound it's going to produce. Okay. Um, so now for this slide here, you just have to read it. Okay. So you don't have to write too much here. Okay. The next slide is, so this one you do have to write. So energy efficiency is calculated as a percentage. And I know that you guys know how to calculate percentage. Okay. I teach it. I teach some of you guys for math. So efficiency is we take the useful energy output, so just the useful one, divided by the energy input, and then times it by 100. All right. So I would say this part here is quite important. Okay. This equation here is very important, and you should write it. So let's try. Okay, let's try this one. So what's happening here is that you have 500 units of elastic energy. Okay, that's the input energy. Benji, oh, can everyone hear me fine? So Gabe said yes. Khalil said yes. Leaf said yes. Um, oh, Benji, I think it may be a problem on your end. Don't worry, I'm recording the video, so maybe later you can watch it again. Okay? Sorry, mate. Okay. So with the trampoline here, the the elastic energy is the input. Okay? That's what you have. And then what's going to happen is that the trampoline is going to push you up in the air, right? And it only give you about 400 units of gravitational potential energy. Okay? So it's not going to give you the whole 500. It's just going to give you about 400. So what's going to happen here, using the equation efficiency, all right? So we put the useful energy here is the 400 gravitational potential. Okay, so 400 put in there over the 500. of elastic energy, then times by 100, and you get about 80%. Okay? So really simple calculation there, guys. All right. Output over input, then times by 100. Okay? And I think that is about it for the law of conservation of energy. Okay? Uh, is there any... Oh, there's a video here. All right, so let's watch this. Okay, so the law says, again, energy is neither created nor destroyed, but is transformed, so changed from one form to another.
Hi, it's Mr. Schnell here. I just wanted to do a little quick demonstration about the conservation of energy and that law. What I have here is just some water in 3 different glasses. These 2 are empty right now. This first one, you can see it's kind of an upside down looking cup. It's kind of a bizarre thing. But I used it as my potential energy starting point. Okay, so I've got the water inside this cup is representing the total energy in my system. So my system consists of these 3 cups. So this water, which is my total energy, right now is contained in the potential energy cup. And I use this cup just because, it'd be pretty easy for it to potentially fall over. So that's kind of the idea with potential energy, is that it can easily fall or, be let loose of a shelf or something like that. So this is my energy.
Sorry, guys.
Right now it's all stored into potential energy. And if I transfer this energy, I can't make more water. I can't make this water disappear. All I can do is move it from one place to another, whether I move it into one of these cups, onto the countertop or the floor or into my mouth. The water is still there. I'm just moving it. And so right now, if I transfer my energy into kinetic energy, now my total water has stayed the same. I only have this much water in my system. This is my total energy. So now all of my energy has been transferred into kinetic energy, which, by the way, is the energy of motion. And so if this water is moving around, it has kinetic energy. Now, I have this other cup with the same label of potential energy on it. Now, the reason I have another cup is that there are multiple forms of potential energy. This one, I was kind of insinuating the idea that this was potential, gravitational potential energy. So it had the potential to fall based on its height or its position. And so what this one could represent possibly is elastic potential energy. So the energy stored in a spring or a rubber band or something squishy like a ball or something like that. It could also be represented as chemical potential energy. So maybe the energy stored in a battery. So now with this kinetic energy, I can transfer it. Remember, I can't destroy it. I can't make more of it. I still have the same amount of energy here. All I can do is transfer it from one place to another. So maybe I'm going to take this moving kinetic energy and put it into my, let's call it a rubber band. So I took some motion and I stretched my rubber band. Okay, so now all of my kinetic energy is in a rubber band. Now it's potential energy again. And I can take that rubber band and I can let it go. And it's transferred again into kinetic energy. And maybe that kinetic energy made the rubber band go higher in position. So my rubber band has a higher height. At the top of its height, it has potential energy. But somewhere in between, it has both. a little bit of potential energy and a little bit of kinetic energy. It's still moving, but now it has a higher height. And so now we can see how this idea of total energy is conserved within the system. There's always the same amount of energy, it's always the same amount of water. Sometimes it's potential as it goes higher up. Now it's all up there, and my kinetic energy is at 0.
Alright guys, so I think I'm gonna stop the video here. It's still got a little bit to go, but I think it's gonna go into the more advanced science ideas. If you're interested, please have a watch. But if not, then I think that should be enough. Um, Now, I hope that this video is kind of helps you sort of visualize what's happening with energy and the conservation of energy, the fact that energy can change from one form to another, and also the fact that the total amount of energy should still be the same. Okay, even when you think about heat and sound being waste energy. All right. Now, uh, so we've gone for over half an hour. It's 9:40. All right. So if you if you need any help with your learning task, okay, or and if you want to ask something about the lesson here, feel free to stay back and ask me questions. Otherwise, I'm happy for you guys to go and do your work. Okay. So this is gonna be so I still we're still gonna have home learning this week and next week. Okay. And then after that, we hopefully I'll see you guys again at school. All right. All right, guys. See you everyone.